Welcome you all to this course on electron diffraction and imaging. We have almost come to the end of this lecture series. In the last few classes, we have been revising some of the topics which we have covered in detail in this course. So, what we have done essentially is we looked at what is the basis for conventional transmission electron microscopy, the operating principle of the microscope, the different modes of operation both in diffraction as well as imaging, like parallel beam diffraction, convergent beam diffraction, Kikuchi diffraction, similarly bright field, dark field and weak beam imaging. Then we came to high resolution transmission electron microscopy. That is what we revised in the last class. In that high resolution transmission electron microscope, essentially what we talked about was that we considered the electron beam as a plane wave which is entering into the sample. As the beam enters into the sample, as it passes through the different regions of that sample, what is essentially is being done is that the potential of the atoms which are there at different positions or the potential of the sample, it is trying to modify the phase of the wave, phase of the incident wave. So, the wave which comes out of that sample at the back of it has got a phase which is different from that of the phase with which it has entered that sample. This is called as the exit wave. So, essentially what we considered that sample as a function, we can represent as a function a, x and y. This is equal to e to the power of phi some function sigma into phi of z or thickness. This phi is essentially the one which depends upon the potential. We wrote phi equal to integral of v x y z dz. So, essentially we consider this as a phase object. Some factor amplitude will come in the picture, but we assume that that remains the constant. Essentially the phase of the incident wave is getting modified as it passes through the sample. This is in an ideal case, but since we are using the lenses, what is essentially that objective lens does it is the objective lens has got some aberrations which are associated with it. They are spherical aberration, then comma, astigmatism, all the rest of it like pincushion distortion, point cushion distortion, curvature of the field, all these things happen. What is essentially important is the spherical aberration. What the spherical aberration does is that it essentially brings about a lot of changes. Before we talk about what all how it deteriorates the resolution, let us first talk about what is spherical aberration. So, in a lens, normally we assume that in a paraxial condition as the beam passes through that sample, that is if the beam is coming from this point and the beam is coming from these points, all these points we assume that at the back focal plane all the rays which are parallel, they are all focused to a particular point and then they form an image in the image plane. And we consider this as a paraxial approximation. What is paraxial approximation is when the beam enters from air to the lens which has got a different refractive index. It has undergoes refraction and that is given by the formula mu equals sin I by sin r. Okay. Paraxial approximation means that if the value of I and r are small, we know from mathematics that sin I can be approximated to I, sin r can be approximated to r, then we can write it as I by r. Okay. This is the approximation which makes all the rays, okay, whether they are close to the optic axis or far away from the optic axis, to be brought to a focus at the back focal plane at a particular point. What actually happens in reality is that the rays which are far away from the optic axis, the sin I, that angle I and r which the beam makes with respect to the lens, okay, is large, because of which this approximation is not valid. So, in such a case, essentially if you wanted to use, we have to, we know that expansion sin I equals I minus I cube by 3 factorial plus I to the power of 5 by 5 factorial, this sort of expansion could be used. So, essentially this is the sort of, only the first two terms are taken, okay, this is called as the third order correction. When we do that, what is essentially is going to happen is that the ray which is coming from here, the ray which is close to the optic axis, it is brought, it cuts at the optic axis. The ray which is far away from it, it cuts somewhere here, because of which what is essentially is going to happen is that for a rays which are emanating from a point, we do not get a point image, instead we get essentially a spread out image in the Gaussian plane. Okay. This is Gaussian plane. So, this approximation we call it as what is its name? So, for a point object, okay, if the object is a point object, at best what we can get is a disk of least confusion, that is the size which we can get it. So, what is the effect of it? This effect of this is resolution is poor, okay, resolution is poor or resolution is limited by that spherical aberration. The next point is that, so essentially what is going to happen is that for an object which is point, essentially we are going to get a disk. Where exactly that image of that object is going to be there, we do not know. These are all the problems which we face, okay, in the case of a conventional electron microscopy. Okay. So, because of this aberration, okay, instead of a point object, we get a disk of least confusion. But fortunately, we know that if we defocus that sample, the defocus behaves in a way where here in this case the ray is the refracted ray is brought closer towards that optic axis. Defocus, what it does, it moves it away from it. So, these two act opposite to each other. So, this introduces what is called as a net phase error, we call it, to the optical part. That phase error is one depends upon Cs to the power of theta to the power of 4 a, okay, minus b a constant, okay, this is the delta f, okay, theta to the power of 2. This is the sort of a expression which we get it for Wg. Okay. This Wg is essentially convoluted with the sample function. Okay. So, essentially a exponential minus I sigma phi z, okay. This is convoluted with e to the power of I Wg, this is what happens. Okay. So, all the mathematics, when we do it, finally what is essentially is going to happen is that with respect to the every scattered beam, finally we will be getting a result that intensity equals, okay, the one which corresponding to the intensity corresponding to a central beam. Okay. Then another factor which will come is to that Fourier transform of this function a will come, okay, and into a term which corresponds to the sin omega g which will come. Essentially what this is going to do is, with respect to this will be a of g. So, with respect to every diffracted wave which contributes to the contrast, okay, depending upon the sign of this, Okay. This can either add to the contrast or it can subtract that contrast, and the net effect of it will be that how many scattered or the diffracted beams can give rise to a contrast, that is what it matters. How we look at it is that if suppose this value of this term is very small, okay, in the sense that almost all the terms have got the same type of a sign, sin omega Wg, then what is essentially is going to happen is that all of them will try to add to the contrast or subtract the contrast, so that in the high resolution image, whatever is the image which we are getting it, okay, in this image, okay, the contrast is enhanced or the contrast is decreased. So, essentially what is going to happen is that either it is adding it or decreasing it, whichever way it does it, it brings about a variation in contrast, and that is the contrast which we observe as dotty contrast in the image, which we have seen in many of these pictures. Okay. Then what is essentially going to happen is that when such a contrast which you are observing it, okay, suppose in some case that value of this, we can see that this depends upon this value of theta. What is this value of theta? The theta is essentially with respect to a lens, what is the diffracted beam or the scattered beam when it reaches lens, what is the angle which it submits. So, it all depends upon that. Depending upon that, this value can change from, if it is sin pi by 2, that Wg becomes, then this becomes 1. Otherwise, if the sign changes, value becomes larger than that, the sign can change, and when that changes for different values, it will be that contrast which we get, we will not be able to explain. All these things we have discussed in the last class. Okay. So, essentially what is going to happen is this spherical aberration one, it is the, for a point object you get a disk of least confusion, that brings about the resolution, and that other effect of it is that this affects, this decides what is going to be the contrast which we get. Okay. Get. So, the third part of it is that when this sort of for a point object we get this sort of an image, we cannot precisely tell where exactly is the position of the atom. From this image, trying to find out where exactly the position of the atom in that sample, it is going to be very difficult. Okay. These are all the problems which we encounter in a conventional high resolution electron microscopy. And generally the value of CS, the spherical aberration, is about something like 2 to 3 millimeter. Okay. Suppose we can make this spherical aberration extremely small. Okay. How exactly it can be done? Okay. As we have seen, the rays which are far away from the optic axis, they are brought to a focus, okay, before the back focal plane. Okay. If we use some quadruple lenses, okay, essentially what it does, it is, we have seen that these quadruple lenses are used for astigmatism correction. Okay. That essentially what we will do, the rays which are far away from the optic axis are affected by that, but the rays which are closer to the optic axis, they are not affected as much. Because of this, they can be used to correct and bring the rays back to the back focal plane. This is precisely what is being done. When the CS is made small, delta F also can be made small. When the CS becomes 0, delta F can be made 0, then this phase error can be made to 0. That means that in such a condition, we are, in that case, we are getting an ideal mic. That is, the aberration is not, the spherical aberration is made 0, or the error which it introduces, okay, in the optical path, that has been made 0, and because of which, for a point object, first a point image could be obtained. Okay. So, the resolution is whatever is given by the Rayleigh criterion, that sort of a resolution we should be able to obtain. The next part of it essentially is going to happen is that this spot is now become a point at this one. So, any small changes in the object, there will be a relatively change in the image also, from which we can measure the position of the atoms. Positions in the image could be measured accurately. Okay. And the third is that all the terms are going to contribute to a contrast. So, we get a much better, sharper contrast. These are all the three advantages, and these three are utilized to get a lot of information about the sample. Okay. Some images are being shown here. Okay. These images I had already shown earlier, but what is essentially one has to see here is that one more point which we have to remember is that using these lenses, quadrupole or hexapole or octapole lenses, we can make the spherical aberration not only 0, okay, spherical aberration can be made negative also, positive, all such things are possible. Okay. Using this condition, essentially one thing which could be done is that now this is a sample where the image is taken from a sample of zirconium, titanium, that is strontium titanium, okay, not zirconium, it is strontium titanate. Okay. In this particular case, okay, if you look at it, in some positions there is an absence of titanium atom position is there, okay, right, not titanium, oxygen atom position, that absence could be noticed. And in another one you can see that this atom has slightly shifted, and that means that the position of the atoms in the image could be measured very accurately. Especially here we know that this strontium titanate, okay, when it exhibits piezoelectric effect, it is in a tetragonal distortion is introduced to a crystal structure. So, the shift of the atom positions could be measured accurately. Not only that, using this we can find out, okay, how many atoms are present along each of this column as the beam passes through. If some atoms are absent, there will be a variation in the contrast. All this information could be obtained very clearly. So, in this particular case also we can see that here that absence of atom is there. All these aspects could be imaged, okay, and we can give correct explanations for it, and using these images we could find, okay, we could get the exit wave function. That is, as I mentioned here, as the electron beam enters, passes through it, only the phase has been modified. So, the wave as it comes out of it, okay, it has a different phase, okay, compared to what it has when it has initially entered, and this phase is called as the exit wave. Okay. Essentially what we consider as image is nothing but that of the exit wave function. That is what we are getting it in all the high resolution images. Okay. This is the great advantage. Okay. So, all these aspects we have covered in detail. Okay. Essentially what we have as I mentioned earlier, okay, and also in the earlier classes, okay, the most important thing is that the resolution, point to point resolution is improved. The consequence of this is that the position of atoms in the image could be measured quite accurately. Okay. The third, okay, is that almost all the atoms, that is normally in a conventional high resolution images, okay, if a heavy element is present, in the presence of the heavy element, the light elements, okay, their images we do not see. Essentially it is the heavy element which contributes to the Doty contrast. Whereas in these cases, from this example you can see that the strontium, which is a heavy element, and an oxygen which is a very light element, all could be imaged. This is the greatest advantage of a high resolution microscopy. So, this is one of the recent advances which has come from the beginning of this century. Okay. This is being used to get information about the samples which was not possible. Like for example, we can get information conventionally when we talk of electron crystallography or crystallography, we essentially assume an ideal unit cell where all atom positions are occupied. But from this technique or using CS corrected microscope, we can get information about the defective crystal structure or the real crystal structure, and this could be used to find out how the band structure changes, all the electronic property changes in real samples. All those informations could be obtained. Recent technique which is being extensively used in electron microscopy is called as the electron tomography. Tomography is a word which you have heard, and you know that computer aided tomography or CAT scan, which is used in medical field to get three-dimensional image of that objects. Either it can be done using X-rays or it can be done using ultrasound, various ways in which it is being done. Similar, why it is being done? Because in a two-dimensional projection, we do not get exact morphology of that sample. For example, in a TEM, if you look at it, it is the sample as the beam passes through the sample, okay, the projected image which we get it on the screen, okay, does not tell, it is only a projection of the morphology which we get. For example, suppose we take a thin disc, okay, and the disc surface is parallel to the beam direction, then what is going to happen is that that image will appear as just as a thick line. Okay. By looking at this image, we will not know what is the morphology of that sample. If we tilt it by a small angle, then we know that this image will just change, become an elliptical one, okay, depending upon which direction we tilt it. Finally, when it is tilted to 90 degree, this will become like a circular one. So, this is a very simple case which we can consider, especially in biological samples, like many of the molecules or proteins structure, so many biological systems, when one looks at it, they have very complicated, complex morphologies which they have. In such cases, to get the true morphology, okay, which is very important for many applications and understanding, is or can be obtained, okay, if we tilt that sample in two perpendicular axes by some small degree, okay, maybe normally what is done by about 1 degree or 2 degrees it is tilted and the image is being taken, okay, and then all these images are stitched, because when these images are being taken, the contrast will be continuously changing. Then there are some softwares which are written, okay, with which one can reconstruct a three-dimensional image of the object which we can reconstruct. That tells what exactly is the morphology which these different viruses, okay, or bacteria or various proteins which they look at the microscope can. The same thing has been used especially in material science also to find out the morphology of the different type of precipitates which form during phase transformation. Okay. Another one which is used quite frequently is to find out the magnetic domains, because we know that in an electron microscope most of the samples which we are looking at are non-magnetic samples. If the sample is magnetic, there is a problem. What is the problem? The lens itself which we are using it in an electron microscope, okay, in the normal case optical lenses are glass, whereas in the case of an electron microscope the lenses which we use are essentially electromagnetic lenses. In an electromagnetic lens, okay, essentially a magnetic field which is being current is passed through a coil which generates a magnetic field, okay. This is the coil current, the magnetic field which is generated, okay, with the north and the south pole along that axis, and as that electron beam travels in the same direction along this optic axis, it is undeviated. But if the beam is inclined with respect to the axis of that field, then what is going to happen is the Lorentz force will be acting on it, okay. This force is what is responsible for the beam to spiral and give, and that is used to generate this or construct the convex lenses. Okay. If the sample itself, okay, where magnetic field is different in different directions, then what will be the effect of that? Okay. Normally, as the beam passes through that sample, the scattering is taking place within the material depending upon the planes which are inclined with respect to a beam direction, whether they satisfy Bragg condition or not. Okay. In addition to it, when the magnetic field is present in this, that will be generating a Lorentz force on the electrons, and this will be changing the direction of the scattered beam or the diffracted electron beam. The consequence of this scattering is essentially going to be that if we get a diffraction spot, this is the central spot and we get a diffraction spot here in a non-magnetic sample. Suppose the sample undergoes some magnetization when we are viewing it or lower the temperature, then this part will be essentially split into few, that depends upon the type of domains and the direction of the magnetization. Now we can put aperture around each of this part, okay, and then try to image the magnetic domains. This is exactly what is being shown in this. Here you can see that depending upon the domains, okay, the diffractor spot has been split into 4. Okay. Using this we can image the domain boundaries, okay, and using these images are called Foucault images. Okay. But essentially what is important is that in this sort of Lorentz microscopy, we can find out how the magnetic domains are distributed like in this example, but we cannot get any information about the intensity of the magnetic field. Okay. And the same Lorentz microscopy is done in a scanning transmission electron microscope also. Okay. This is another technique. Here also one can image the domains quite nicely. Okay. Because so far whatever we have covered was conventional transmission electron microscope, okay, where the beam is falling onto the sample and the beam which is scattered, okay, they are scattered in different directions, okay, because of the crystallinity of the material, okay, and these scattered rays are brought to a focus at the back focal plane, okay, where the diffraction pattern we get it, and in the image plane we get the image. Okay. Another way in which we can do the same images which we can obtain or the images of the sample is that if we make the beam, okay, into a very fine beam, okay, this is possible because of the advent of FEG, that is field emission gun, which gives very good brightness, and since the aberrations could be corrected, we can focus the beam into a very fine point of the size of around 0.2 to 0.1 nanometer, okay, and this beam, okay, can be made to scan on the surface of the sample. As the beam hits at this particular point, okay, the beam is scattered, okay, and the transmitted beam and the diffracted beam will be coming. These beams could be separately collected, okay, using detectors, okay, and effectively that if we scan the beam from point to point and the transmitted beam is collected by this detector, okay, depending upon the how much is the scattering which is taking place in other directions, there will be a variation in intensity of the beam which comes out. This will give rise to a contrast. Like in an SEM, we can get an image, okay, and with very high resolution. This is what is done in a scanning transmission electron microscope. And the diffraction, if we collect the images which are coming to this annular detector which is being used, okay, then this will give rise to a dark field image of the sample. Some of the examples is shown. This is a bright field image of the sample, and this is the dark field image. This is the diffraction pattern which has been obtained. Okay. And the advantage of scanning and transmission electron microscope is that in the normal sample, Okay, as we had seen, the contrast arises because if a there is a bending of that sample is going to be there, then that gives rise to some dark contrast. All those things does not affect the contrast in scanning transmission electron microscope. So, we are able to get relatively a much better uniform image, and especially when we wanted to find out the particle sizes and all, okay, this image could be used to get correct information. Okay. The details of it I have covered earlier. Okay. So, I will not go into it. Okay. Another important information which we can get it in this microscope is that when the beam is falling on that sample, okay, and we are making it move from one region to another. As it moves from one region, shifts to another region, okay, we are able to collect a diffraction pattern from each of this region, okay, and another from this region. Like from every point where the beam is falling, we can collect an independent diffraction pattern. If we analyze the diffraction pattern, we can get information about the orientation of the beam, the orientation in the sample, that is from region to region. If there is a variation in orientation of that sample is going to be there, that would be done. So, this is called as the orientation imaging microscopy. Okay. This is similar to the EBSD image which is obtained in the reflected mode in scanning electron microscope. Okay. In this also one can get an angular resolution of about something like 0.5 degree to 0.01 degree, okay. And then the area which we scan, okay, could be some micrometer square to millimeter square, okay, and the beam sizes could be, the lateral resolution could be from something like 20 nanometer to 100 nanometer. Okay, with this resolution, okay, we can get information about from region to region. If there is a small misorientation of about 0.5 degrees, that could be easily measured. Okay. It is an elastic scattering, but what is essentially is going to happen is that in this scattering, this is it is essentially an incoherent scattering. And more than that, the intensity of the beam in specific direction depends upon Z, that is the atomic number of the element. Suppose we assume that, I think with this slide which we can see it here, is that there is essentially, as it is being mentioned, the bright field, okay, detector could be used to get information about the bright field image. Annular detector, dark field detector could be used to get this information, and the influence of the effect, the Rutherford scattering, that could be collected by what is called as a Haddif detector, that is high angle annular dark field detector. Okay. This essentially happens when the scattering angle is more than 50 millirads or more. Okay. In this case, suppose we assume that in that sample, okay, from specific region, this region, okay, some high Z element is present surrounded by a low Z element, okay, and in this large angle which it makes with respect to it, from this high Z element, okay, the intensity of the signal which is coming is going to be large, which is depend upon the Z, whereas the low Z element which is there, the intensity of the signal which is going to come from here in this direction is depends upon Z. So, because of the variation in Z, since the intensity depends upon Z, that gives rise to a contrast. Okay. This contrast could be used to get information about how different elements are distributed in that sample. Not only that, and since I mentioned that the beam in scanning transmission electron microscope can be focused to 0.1 to 0.2 nanometer, which is almost of the order of the atomic resolution, we can make the beam scan across column by column of the atom. So, as the beam passes through here, if the atom is going to be there, the transmitted direction intensity will be less, and in the in between region the intensity will be more. Essentially a sort of a lattice resolution image which we can obtain. Okay. That is what is being shown here. Okay. In this specific case, it is essentially a multilayered sample which contains silicon, germanium, okay, silicon, germanium, like that is happening. And in this case, you know that the silicon and germanium has got different atomic number, because of which we can see that the contrast, there is a variation is there. So, essentially what is being done is that using this Rutherford scattering or using this high angle annular dark field detector, we are able to get, okay, image at which region which type of elements are distributed. Okay. But still we should have some idea of the type of elements, because this can only tell that depending upon the intensity of the signal, okay, which is coming, or the intensity of the image, we can tell whether it is a high Z or a low Z element. But to find out which is the particular type of an element, we may have to use, okay, either yields or EDS. Okay. Using that, we can find out which specific element is responsible for it. So, essentially using a combination of various techniques, okay, we can get information about how elements are distributed. Not only how the elements are distributed, we can get information about this distribution almost on an atomic scale, that is along the column how the variation is going to take place, okay, from region to region, and an atomic resolution of distribution of elements could be obtained. But using this, still we have not reached a stage where we can find out at which position in the sample the atom is sitting. For example, in this particular case, if we see here, we can notice it that in this position these regions are bright, which corresponds to antimony, okay, is present along maybe in this column which is sitting there. That is what that information. But in that column, whether the antimony is sitting here and in this region or in this region, that is going to be extremely difficult. But in the lateral resolution or the lateral space of that sample, we can find out in which specific location these atoms are distributed. That information we can obtain. Okay. Okay. Another important technique which has come is what is called as the electron holography, because as in this class I started with talking about high resolution microscopy. Said that using high resolution microscopy we can find out distribution of that atom positions. Okay. That is what our aim is. Why do we wanted to do that? Okay. This is to find out, okay, which positions atoms are occupying, okay, in the unit cell. Okay. In the crystal we wanted to get that information. Okay. But generally what happens is that when we get the image, okay, we know that the amplitude essentially is a complex function, and because of that the size I star, okay, the information about the phase factor is completely lost. Okay. So, what has but what we have done it is that in a high resolution microscope, this phase information we have tried to convert this into a contrast. Okay. So, if we can try to quantify the contrast, then we can get some information about, okay, the phase of the wave, okay, exit wave. For that, what it has to be done is that we have to assume a model of that sample, okay, and then go about and do it. and many images have to be taken in a conventional high resolution image, okay. And then we have to do an image simulation, then only we can get information about, okay, the crystal structure. Okay. The same information can be obtained in a much more elegant manner, okay, using electron holography. Hologram is a technique which has been invented in 1950s, for which Gabor got the Nobel Prize. What is the principle of a hologram? Essentially, as a coherent monochromatic beam passes through a sample, okay. Suppose it is a sample which is there, as the beam passes through the sample, okay, what is essentially is going to happen is that, depending upon the refractive index of the material, okay, some phase difference will be introduced. As the beam passes through different regions, different phase differences could be introduced, okay, in different regions, and the rays which come out will all be coming out with different phase, different phase. Okay. If this beam is split into two, and this is called as the reference beam, if we allow these two beams to interfere, then what is going to happen is that the interference pattern which we get it, or that is called as the hologram, okay, that contains information about the phase, that is the contrast which is going to arise depends upon what is the sort of a phase difference which has come at different region with respect to the reference beam. Okay. This is how a hologram is made. Okay. The same principle is used in a electron microscopy also. There are many types of holograms which are being made. Okay. They are called on-axis hologram, okay, off-axis hologram. There are various types are there. Essentially, what is being done in an electron microscope is that beam is made to, part of the beam is made to pass through that sample, okay, and different regions as the beam passes through. As we have seen that exit wave, the phase has changes depending upon the local variation in the composition of that sample, okay, and this is the reference beam with which, okay, this is being made to interfere, okay, split into two and interference is done, and then this is being made to interfere with the reference beam, okay. Then the type of an interference pattern which we get it, this is called as the hologram. This pattern from region to region as the contrast varies, okay, that can be related to the type of phase which has been introduced, okay, to the incident beam at different regions of that sample. Okay. Okay. This sort of phase difference which we talk about, okay, in the case of a sample could be introduced by either the electrostatic potential, okay, variation in electrostatic potential, or in the magnetic potential. Okay. So, using, and not only that, this contrast which we are getting it, okay, or the variation in intensity could be quantified, and that could be related to the magnitude of the electrostatic or the magnetic potential. Okay. So, as I mentioned earlier, in the Lorentz microscopy, okay, we can find out the magnetic domains, but we can find out the intensity of the magnetic field and the direction. But in the case of electron holography, we can get not only we can get the domain information, but also the direction in which the electrostatic field or the magnetic field. That is, in the case of a magnetic material, it is a magnetic domain information. In the case of a piezoelectric material, okay, or ferroelectric material, okay, there we can get information about how the ferroelectric domains are distributed, also how the intensity changes, all that information which we can obtain. Okay. This is essentially a holographic image from a magnetic cobalt particle. Okay. This I had shown earlier, just I am repeating it again to just make sure that you can recall what has been described at that time. Okay. And here you can see that these sort of fringe patterns which are coming, and another is an interference pattern which are coming. This is the reconstructed image, and from this we can make out how the magnetic field is distributed within that sample as well as the outside of that sample, how the field is. All those information could be obtained. This is an image which is taken from lines of force in a magnetic medium. Okay. Especially when a lot of work is being done, okay, on memory materials. Okay. The electron holography technique in TEM is extremely useful to find out, okay, how the different domains are distributed, and this can be used to increase the capacity of that memory material. Okay. For those applications, electron holography can be used. If you look at a microscope, we have various types of microscopes. There are conventional transmission electron microscope, okay, then analytical electron microscope, then high resolution transmission electron microscope, then we have CS corrected microscopes which are very common now. Okay. Then microscopes which have with electron holograph. These are all independent microscopes which are optimized for getting the best information. Okay. These sort of microscopes are available. Okay. Other than that, the recent development in the last maybe 5 to 10 years is in what is called as a pulsed electron microscope. Because what happens in all these microscopes, the electron beam is continuously falling on that sample surface, and as the beam passes through, many of these samples are electron sensitive, and the high energy electron beam can damage the sample, especially in the biological samples. Okay. In such cases, by the time we examine that sample and image, okay, the information which we are getting is the about the sample which has already been damaged. To avoid this, what is being done is that the incident electron beam itself can be pulsed. Okay. Monochromatic beam is pulsed at a particular frequency, so that of a very small pulse duration, maybe nanosecond pulse duration. As the beam passes through that sample, you record both the image and the diffraction pattern. Okay. And then as progressively as the beam passes through that sample, we can get information about how the electron beam is modifying the sample. That information could be obtained. Okay. This has a lot of great advantage in biological samples. Okay. Not only that, we can get information about how the electron beam is interacting with that sample. That information also could be obtained from those images. Okay. So, these are all the development. Essentially, all these developments have taken place because as the beam passes through the sample, different type of interaction the incident beam has with the sample. So, one has to identify what is the way in which it is interacting with that sample. On that basis, okay, or one can create a particular setup to collect that information, and that information collect and that scattered information will be able to give some specific information about the samples. And this is all left to you people, how you wanted to take this field to different heights. Okay. So, essentially what I have done is reviewed the different types of microscope, okay, or whatever I have taken so far in this class, okay, including conventional microscopy, high resolution microscopy, okay, also the recent trends in various electron microscope, okay, recent trends in the transmission electron microscope. Okay. I will stop here now. Thank you.